Right. Hello everyone. Welcome back to Linear Algebra done right by Sheldon Axler. So last time we left off at question 27 in section 3b. We technically finished all the questions in 3b, but 27 was the one question which there was a much better way to approach this question than what I had in mind. I had to look this one up. I mean, there's so many questions in the book. I can't do every single one of them, so occasionally I have to look one up. But this one, the way they thought about this was such a linear algebra way that is completely foreign to me. So consider this sort of situation, right? You have a differentiation map from polynomials to another polynomial. So the way they thought about it is thinking about dimensions. In fact, Q has to be, so let's say polynomial P has degree n, then Q has to be a polynomial of degree n plus 1. Maybe take some time to convince yourself of this, but it's true, because if the highest power of P is n, then that highest power must be taken as some sort of derivative of some degree n plus 1 for that to get there. So you want to consider that to be the case. Then you want to consider the function, or the linear map rather, which represents this. The fact that it's surjective over the entirety of, so every polynomial of dimension n or less can be covered, means that it's surjective over such n dimensions, right? It's probably best to use n minus 1, because like this always comes up as talking about polynomials. It is of degree n, but it has dimension, the vector space spanned by all polynomials less than or equal to degree n is n plus 1. So you have to be careful about the distinction. Rather, let's continue with this, because then you will just simply want to show the dimension of the range of this linear map has dimension n, and then you're done, right? Where n is the degree of the polynomial P, right? Once you're able to show this, then any such polynomial P can be expressed as a linear map on a certain input inside of, let's say, dimension n plus 1. Because we're talking about the derivative map, it should probably be n plus 1, right? So what gives you like that kind of intuition? Well, first we have something like the fundamental theorem of linear maps, which just keeps on occurring through this chapter, because I think it's really the only thing that we've learned that allows you to deal with such kind of things. So ideally, the dimension of the kernel plus dimension of the range is n plus 1, which is the input space you're coming out of, right? The input space you're coming out of is polynomials of degree n plus 1, and you're going to polynomials of degree n through the differentiation map. So ideally, if you're able to somehow show that the dimension of the kernel is 1, then you're done. Or potentially, if it's less, then that's fine too, but then it wouldn't, the differentiation map wouldn't work, because if the kernel is dimension 0, then you would map from a space of dimension n plus 1 to another space of dimension n plus 1, but you just don't have space for that in the differentiation map, because you squash down dimension, right? So we somehow got to show that the kernel of such a map is 0. As long as you're able to do that, you're good. And this is quite sensible, because, applying the definition of a differentiation map, the dimension of such a kernel is 1. The reason is because if you take the derivative of a constant, you're going to arrive at 0. and any higher order polynomial, like of degree 1 or 2 or above, you would get something that's not 0. This is pretty easy to think about, because if you take a polynomial that has degree more than 1, and if you take a derivative, you're not going to get 0, but instead you're going to get at least the linear term will be squashed down to a constant, and that constant is not 0. In the case of polynomial degree 1, polynomial degree 2, then the coefficient on the squared term will be squashed down to like 2b and 2bx and so on and so forth. Right, so I guess that's 27 demonstrated, because to sum up the argument, you want to show that the kernel of the differentiation map has dimension 1, which is just true by the definition of differentiation map, and examining it. And the dimension of the range of the differentiation map is then completely determined by the input space, because what we know from the fundamental theorem of linear maps, which gives you that much information. So yeah, I guess they were right. It is more fun to do it the linear algebra way, but it also requires so much understanding that it completely went over my head. So, I mean, at this point, it's a matter of, if I really want to solve all the problems in this book, then I need to devote at least 20, 30 hours a week to doing this, because just thinking about it on the off chance that I get some time is not enough. And it won't be enough to really understand what this linear algebra stuff is all about. So hopefully I'll be uploading a lot more and doing a lot more problems that way. Because if you think about it, like, going to school is just a matter of learning and forgetting, and if you don't put it upon yourself to really learn about the intricacies of this thing that you're doing, then it's a waste of time and money for everyone involved, and sometimes you just gotta think for yourself. And for me, I think this might come at the expense of the grades in my other subjects, stuff like that. But if this is important to me, then that's just what I have to do. Anyways, so let's continue with exercise 3C1. Suppose V and W are finite dimensional, and we have T, which is a linear map from V to W. Show that with respect to each choices of basis in V and W, the matrix T has at least dimension range T non-zero entries. Okay, so to understand like what this question is talking about, first you gotta understand what the matrix representation of a linear map really is, right? So the matrix representation of a linear map. Let's say you have a linear map from V to W, name it T, then the matrix of such a linear map can be represented as, let's say something like this, right? And then what they're really talking about is that if you have some like, and actually this matrix, the way the matrix is represented will depend on the basis you choose in vector space V and W. There's a different spaces, you will get a different matrix, of course, because the reason is this matrix is just a condensed way of showing you how to transfer one basis in V to one basis in W. And if you change the basis, then that representation of how you shift from one basis to the other is also going to change. So, and of course, like a condensed way of thinking about it is, I mean, if you have a basis in V, you have a basis in V and a basis in W, and I won't write them out because I'm too lazy to, then the linear transformation of V1 would be A11, W1, etc. plus AM1, WM, right? And that's the way this matrix thing works, is that this thing is supposedly T of V1 expressed as a linear combination of the basis in W. And once you get that far, you should be able to do this, because imagine the contradictory case, right? Imagine if the matrix T has at least, so first you gotta establish some premises. So let's assume that dimension of range T is actually K, right? It has dimension K. Then what you know is that at least K of these columns have got to have non-zero entries in them. And here's the reason why. If you have less than k columns, that are non-zero, then what you're really looking at is, let's say you have some, let's say that for argument's sake, without loss of generality, you have some, oh shoot, am I doing this notation wrong? Yeah, I think so. Let's say for some, I don't know, L columns, you have some sort of non-zero columns, and everything after is zero columns, right? Columns full of zeros. And then these first k columns are going to give you actual, let's say, how do you call it? Actual values in W, right? Because what this is really saying is that for tbk plus 1 and tbk plus 2, etc., and stuff like that, all the tbk plus 1, tbk plus 2, all that stuff is equal to 0, right? So you have more than, let's say, more than, say the dimension of V is n, and the dimension, or the number of columns which are non-zero is greater than n minus k, where k is the number of columns, where k is the dimension of range T, right? So if you have number of columns where things are 0 is greater than n minus k, the number of columns where there exists one non-zero entry is less than k. So then you have the situation where number of columns where you have all zeros is greater than n minus k, then the kernel of the transformation has dimension, let's say, greater than n minus k effectively, right? And then the range is doomed to have dimension less than k, because these two have got to sum up to n. And this sort of is contradictory to the fact that dimension of range T is k, right? That's per our assumption. I think the situation is sort of saying, like, if you just have a bunch of zeros at the right end of your matrix, that's just going to signal all of those vectors in your V basis are mapping to a bunch of zeros, right? And all of them are getting squashed into the 0, whereas all the basis elements from V1 to Vk are getting mapped to actual non-zero meaningful values in W, perhaps. It's not guaranteed, but you could have well, no, if W is a basis, then okay, but it's not relevant. The relevant thing is from Vk plus 1 to Vn, you're getting mapped to 0. And you don't want that k to be too small, because if that k is very small, then a lot of things are getting mapped to 0 here, which you don't want. Because if you have too many things mapped to 0, your space is getting squashed, which is why here you gotta have at least range T non-zero, dimension range T non-zero entries to at least get that range T, right? Not the best explanation, but I'm trying to do 20 linear algebra questions in one morning, so it's not exactly going to be precise. So let's consider D as a differentiation map defined by, so you have the differentiation map on some polynomial and you choose basis. Okay, so this is fine. Let's say you naively chose the standard basis for each, right? 1x, x squared, x cubed, and then for polynomial degree 3 or degree 2, you get 1x, x cubed, right? X squared. And then the matrix that maps from this basis to the other, you just get, let's see, what the way they use this is very confusing, because actually I think what's going on here is this last one is actually transformation of 1, because the transformation of 1 gets mapped to 0, right? So what you actually want to do is kind of weird. You want to like swap these things around. By the way, if you haven't seen something like this before, I'll just briefly draw it because I think it is useful. Because there's something like this, right? You have so your basis in W and your basis in V. And then the transformation of V1 is found by performing linear combination on the basis of W with the entries from the corresponding column. So it's a pretty cool trick that you should know if you like do problems a lot or read the textbook. And I mean like thoroughly read the textbook, like fanatically obsessed about it, then obviously this will become obvious. But if not, then this might be news. So of course you have, let's say you have a linear transformation and then you naively put down a basis, but then you realize that this column's got to be 0, so you put 1 down here because like I said, if the column is entirely zeros, that thing that you put down, like this basis element, is going to be mapped to 0, so you want to put this here, x squared x cubed. And then here what you have is probably 1x x squared, presumably. Like this is a basis of W, this as a basis of V, and this mapping what you have is 0, 0, 0. So if you take a derivative of x, which is a linear transformation, then what you get is 1, right? And 1 is 1 times 1 plus 0 times x plus 0 times x squared. So what you do is you take those coefficients and reverse engineer out the column, what the column should be. The same thing you can do is x squared is 2x, so you get 0, 2, 0, and then the same thing was this. But then you notice like this isn't quite right, so what you do is you gotta rescale the basis in either P3 or P2. I think P3 is easier, or maybe maybe I have a misconception, but it doesn't matter because it is a solution nonetheless. So I think that this already works. I'm not going to confirm it because I have in the past probably, maybe. Let's go straight to question 3. Suppose V and W are finite dimensional and T is a linear mapping from V to W. Prove there exists a basis of V and W such that with respect to these bases, all entries of the matrix of the linear transformation are 0 except the entries. And so basically the main diagonal up to a certain point, and then it's just all zeros everywhere, right? There's a couple of things to think about here. So particularly you want to focus on V going to range T. So without like too much fanfare, I'll just directly introduce the concept. The basis, you can establish a basis for range T, and what you get is W1 through WK, let's say. Let's establish that dimension of V is n, dimension W is m, and dimension of range T is k. And then what you have here is these things are all in range T, which means they must all have corresponding V's that such that T of such V's is equal to W, which is quite fine. So you do that. And here's the interesting part, right? Because these things are linearly independent, so must be 1 through Vk, right? Because if these things have a linear dependence, then that means there's a non-trivial linear combination amongst these W's, which the transfer, so then there also is a linear combination within these V's, which is non-trivial. I've thought about this for quite a while, so I'm not going to explain too much into like why I thought about that way. But the basic gist of it is you're going to get this, right? And then that means, let's see. Yeah, so then the linear transformation of this is 0. Oh wait, did I do this the other way around? Because I think one of those things is true, like, I mean, think about it this way, right? If you have a basis in W of the range T, this is a basis of range T. You also have a basis in, not necessarily basis, a set of vectors in V that currently maps to those W's. Then what you have is, one set of those relations must be true, that if these things are linearly independent, then so must these, or it's the other way around. If these things are linearly independent, then so much those. But there's a obfuscating factor here, which is that the kernel of V could be not just 0. And in that particular case, of linearly combination of this when put into the transformation will be 0. And that's the obfuscating factor here. So in fact, I think I've actually written a document detailing this exact scenario, but I have already forgotten it, so I need to check back. So let's say you have a basis in V and a basis in W, and you're mapping from V to W. And you take the situation exactly as we did. You have a range of T which is resting inside W, and then you form a basis of it, and then you find the V's that map to it, right? So if these things are linear independent, it does not imply, okay, so this way doesn't work. I think the other way does work, right? So if TV1 through TVK are linearly independent, then V1 through VK are forced to be. The reasoning I gave here is because if TV1 through TVK are linearly independent and span a space of dimension k, then so must V1 through VK, because V1 through VK actually mapped to TV1 through TVK. You have something like the phenomenon theorem of linear maps, which says that, you know, your input space can't be smaller than your output space, otherwise you're not going to stretch and reach all those dimensions. So I think that's a very quick and efficient way to see that. So I had doubts there because that's just what mass is. Like, if you thought about something one morning, 2 seconds later you're going to question it. So, if you have W1 through WK, then obviously, not obviously, this is not obvious at all. It took me hours to figure out. V1 through VK is linearly independent, right? Where TV I is equal to WI for all I between 1 and k, and so on. So you have that V1 through VK are in fact linearly independent, which means, and this is very important, you can extend these two bases to full bases in V and W, right? And once you are able to accomplish that, you're done. You're basically done, at least. So what we can do is just say that, well, the basis I want for V is going to be V1 through Vn, where it's a extension of the basis V1 through Vk, and the basis I want for W is basis from W1 to Wk, or Wm rather, where it's a extension of the basis of the range of T from W1 to Wk, and then the transformation of V1 is just 1 W1 plus 0 times everything else, so it's just 1 0 0 0, and and the rest goes the same until you reach Vk, where you get your last 1, and the rest of the matrix is just a bunch of fat zeros. And then that just works. And think about it this way: everything from Vk and up to Vm must map to 0 now, because this space V1 through Vk is in the kernel of V. The rest must, V1 through Vk is in the range of V. The rest must be in the kernel of V. Those two things are exclusive. So they must map to 0, and then 0 is 0 w1 plus 0 w2 and so on. So that entire column going that way is zeros. Let's go through question 4. Suppose V1 through Vm is a basis of V and W is finite dimensional. Suppose T is a linear mapping from V to W, then exists a basis V1 through Vn of W such that all the entries in the first column are 0 except for possibly 1 in the first row, first column. Okay, this is not terrible because you're just thinking about the first column, so you don't have to think about any other columns. And you want is there's potentially 1 here, but the rest have got to be zeros, right? This is what you want. And then what you have to do is just to say T of V1 is equal to W1. That's all you have to be able to manage, right? And you can't have a case where if T V1 is equal to W1, you have a strange linear combination of this that's somehow equivalent. The reason is because if these two things are the same, you now establish a non-trivial linear combination amongst W's, which isn't possible because W is supposed to be a basis, right? Those W's are supposed to be basis of W and therefore linearly independent, so you can't have that. Therefore, if they give you a basis V, a basis for V, like V1 through Vm, all you gotta do is find what T of V1 is, call it W1, and then just, put it there and then extend it to a full basis of W, and then you're done. I think it's not don't overthink that question, I guess. It's not a very sophisticated question, or at least I don't think it is. So then, this is the other way around, where you suppose you have a basis of W and you want to find a correct basis for V such that you got this first row being all zeros except for the first entry, which is allowed to be 1 potentially. I think that you do something very, very similar where you say, well, oh, wait a second. Yeah, man, it screwed up on this one. So they gave you the basis in W, which is actually much more difficult to do. So let me just write this down. First you got W1 through Wm going this way and V1 through Vn going this way, right? And then what you know is that V1 is expressed as potentially 1 or 0 W1 plus a bunch of junk, and then V2 is expressed as definitely 0 W1 plus some other stuff, and Vn is expressed as 0 W1 plus a bunch of stuff, right? So V1 can be, so there's two scenarios. Either V1 is inside of the range of T or it is not. And if it is in the range of T, then you can find the V such that T of V is equal to W1. And then you just put that V in the first element of the basis of V and expand it to the full basis. And I think you'll be done there, maybe. But if you say that W1 is not in the range of T, then it can't form a linear combination with other things, with other W's which are in the range of T to arrive at T of Vj, for example, because it wasn't in the range of T, and the range of T is a subspace, so it's closed with respect to addition, so you can't have that. So you got two scenarios. If it's not in the range of T, then everything is just zeros. If it is in the range of T's, then the first element is 1 and the rest are zeros, and I feel like that's a secure way of understanding such a problem. But then maybe something else needs to be explored here, is that why some arbitrary VK in here, for example, not equal to 1W1 plus a bunch of other junk, right? Maybe that's something worth exploring. Yeah, this is not entirely clear. I think I require more thinking on this matter, but I'll get back to it later. Yeah, I will note this down and get back to this. Just maybe an intricacy that I missed in this problem here. So what if Q5? What if VK, T of VK is expressed as 1 or some, I don't know, it doesn't have to be 1, C1W1 plus a bunch of other stuff, CKWK. My suspicion right now is that if it is indeed expressible as those other things like C1W1 through CMWM, where the coefficients C's are not trivial, then it should also be expressible without this W1. The reason I state that is because if you think of like T of V1 being mapped to W1, then each specific V should target a specific W, and you should be able to construct this VK without the introduction of any previously used W's. They should be linearly independent in that particular way. But maybe I have missed something on that matter to revisit that. Alright, let's consider question 6. Suppose V and W are finite dimensional and T is a linear mapping from V to W, and prove that dimension of range of this linear transformation is 1 if and only if there exists a basis of V and exists a basis W such that with respect to bases that the entries of matrix equals 1, right? I'll just write a 1 here because this is what sometimes math people do, I think. Instead of writing a bunch of zeros or ones in the matrix, they just put a 1 here, indicate it's all ones. And then what you have here is, you want to show it this way and then that way, probably. So we'll go the first way, from left to right first. So we'll say that if dimension of range T is equal to 1, then all entries in the matrix is equal to 1. And well, there you can establish a basis such that the matrix with respect to the basis and the linear transformation gives all ones, which is fine, right? But the problem lies in how do you find that particular basis. This doesn't seem so obvious at first. So here, before you even do any of that, before considering that they are all 1, think about it this way, right? If T V1 is equal to C1 through Cn and so on, think about how they're all squashed into one dimension. TV1 through TVN, they're all being squashed into one dimension in the vector space of V. That means they must be scalar multiples of each other, because they're squashed into one dimension, and you can form a basis of that one dimension using some arbitrary vector from that dimension that's not 0, and everything is then a linear combination of that vector itself, which means it's a scalar multiple of it. And then what you have here is that every single every single tb1 through tbn here is a scalar multiple of tb1 in some way. And what you're then able to do is pretty magical, because if you have tb1 equals to c1w1 through cmwm, then tb2 is forced to be a scalar multiple. Let's call it alpha c1w1 through cmwm, and so on. Then in here you have maybe alpha and minus 1 of the same. What you're then able to say here is that in a strange way, this like makes things a lot easier. So first, you don't want these to be C1 through 3m. You want these all ideally to be 1. So let's make that happen, right? We'll establish a new basis. So let's say TAB1 is equal to C1W1 plus through CMWM. For this, we want to establish the new basis such that VI prime is equal to VI over C I. And then this is just fine for all I between 1 and m, right? Then you have these new WI primes. And these new WI primes then allow you to say that this is just 1 WI prime plus etc. through 1 WM prime. And this is fine because the transformation of any such V I will have the effect of being a linear combination of some scalar multiple of 1 W1 prime 1 times, so basically 1 times everything, right? And then you scale the V's now. So V1 is fine because that's how we defined everything, and V2 we'll do V2 prime is equal to V2, V3 prime is equal to V2 prime is equal to V2 over alpha, and V3 prime is equal to V3 over alpha 1, and so on. Then you're able to accomplish all of that, and then with the new basis, what you're able to do is finally claim that you have established a basis where let's say V1 prime through Vn prime maps to W1 prime and Wn prime with matrix entirely 1. And it's just how we define everything, so I'm not going to explain more in that direction. But you have all entries of the matrix equal to 1 with some basis in mind of V and W. Then you want to prove that dimension of ranges of T is 1. And of course, like, I think this is a strange situation where well, actually it's not that strange, because going backwards is just much easier. There's nothing interesting about it. Well, not quite as much, I think. I think most linear algebra questions are somewhat interesting, but this one is not. Going this way is not too much in that direction. So then you like just naturally have that TB1 is equal to 1v1 plus 1v2 etc. plus 1v let's just say, because previously I used n for both and it's not necessarily true they have the same dimension. So TB1 is equal to all that stuff is equal to TB2 is equal to TBN. And then what you have here is that TB1 is equal to TB2 is equal to TBN. And so TBI is equal to TBJ for arbitrary ij between 1 and n, and so on. So it's pretty clearly mapped to the same dimension because in fact they map to the same value. And anything in the range of T can be expressed as a linear combination of these TVIs. So in fact, then it's just a linear combination of the same, let's say, linear combination of TB1. So it's then just a scalar multiple of TB1, which means like indeed range of T is spanned by V1, which means it's just one dimensional. That's perfectly reasonable to say. So let's verify question 3.36. Right, so the matrix of the sum is the matrix of the sum of linear maps. So this one I almost don't want to do because if you understand the definition for a matrix, which is derived from the motivation of linear maps, then this almost becomes too easy. But if you don't, then it's really hard because you haven't like thought about it properly, which that was me a while ago. So all you gotta do is just think about it this way, right? So think about it in terms of columns. Let's take the case column of both S and T. I don't know how the textbook notates it. I think they just put an empty space before the comma and then put the column value after the comma. I think that's how they do it. Yeah, but let me check because I don't remember. Okay, never mind. I don't think I can find it, but it's fine. Like, I don't think it's a big deal. Okay. So you're adding element-wise the columns of S and T to arrive at the columns for S plus T, the case column of S plus T, right? And this makes sense linear combination-wise because S is a linear combination from linear transformation from V to W such that you have, let's say S1K, so T of Vk is equal to S1K plus W1 S2K plus W2 and so on as MKWM, and T is very much the same. TMKWM. You add together and then it just becomes this. And if you restore this back to the matrix form, which you certainly can, and in fact I think is what you're supposed to do, and then this just is indeed a column-wise is an addition of those two columns where you have a set theoretic addition or something stupid like that. Okay, so I guess that's question 7, and we'll go in for question 8, which says verify 3.38. Yep. A matrix of a scalar is the scalar times, no, the matrix of a scalar times a linear map. So yeah, I think like this is basically trying to show that all the properties of a linear map are preserved when you transform it into a matrix, which definitely makes sense because the coefficients in the matrix I think uniquely identifies a linear map. So there's like a one-to-one mapping there you can think about perhaps. But without even going that far, it's probably just evident by looking at the operations of columns and stuff like that. So then let us consider once again some arbitrary column of M, because once it's true for some arbitrary column, it's true for all columns, and then that encompasses the whole matrix. So then thinking about it this way, let's say T of Vk is equal to some lambda, let's say some lambda W1, or maybe I should M1K W1 sort of lambda times MK WM. That's a lot of M's. Okay, so if you add them together, you're gonna get T of Vk. But if you break out the lambdas, then I think I screwed something up. No, it's fine. Yeah, so in fact you can factor out the lambda out of every column inside of the matrix, and then it just becomes lambda times that matrix, because that's how scalar multiplication of a matrix is defined. And these two things are equivalent to each other. So having a scalar inside the matrix is the same as having it outside, and then you're done, right? Yeah, once again, these proofs are really rough because I'm not really giving proofs, just ideas of proofs. I don't have time to do all that. So if A is an m by n matrix and C is an m by 1 matrix, and AC is equal to C1 times the first column of M, the first column A, etc. through Cn times the first column, or the nth column of A, rather. I don't think there's much to prove here. I don't think. Well, the thing is they haven't introduced vector and matrix multiplication, which then you have to rely on the definition of a matrix which is based on the linear map itself. So considering this, that maybe there is some difficulty to it, so I'm not sure. Let's think about it this way, right? C is some arbitrary element inside some vector space of dimension n, let's say. Maybe less than dimension n, but I don't know. But then what you have here is, because you can have a subspace inside a space of dimension n of less dimension than n, which is perfectly fine, or something like that. I don't think it matters here. So the linear transformation from C to the output, which is probably an FM space, I mean, it's probably signified by, this is so much easier if you can define matrix multiplication. I mean, gosh darn it. Well, let's just assume that matrix multiplication is defined, because they have defined matrix multiplication between two linear transformations, just not between a linear transformation of vector itself. I think that there's something weird going on, but I'm not sure how that definition will proceed. So let's say you have a matrix that looks like this. Yeah, M1 going through Mn. Okay, so let's say you establish a basis in the space which you are mapping to. So let's call that space W, and establish a basis W1 through Wm. Then this linear transformation is called T, which the matrix is representing. Then T of C, which is this vector here, T of C is going to be equal to so let's decompose C into its linear combination within the space which it resides, which is from, let's say, V1 to Vn. And then you can say, like, this is the transformation of V1 plus, like, Cn times the transformation of Vn, etc. And this, individually speaking, is C1 times A11, W1, etc. through A, M1, Wm, and so on and so forth. Indeed, if you think about W as being the standard basis of some arbitrary vector space some vector space over an arbitrary field f raised to the power of m, then this does work, I think, for the sole reason that then you are just multiplying by the column vector. So for example, this entry here is the column vector a11 through am1. So it's just c1 times. I mean, this seems to work, and like obviously, I don't. Okay, no, like every time I say the word obviously, I want to like remind any potential audience here that it probably spent at least 2 or 3 hours thinking about it, so I shouldn't say it's obvious. I keep saying things are obvious when they are not. So first you have so let's say you assume the definition of matrix multiplication was a vector, which wasn't defined in this first portion. Then this entry goes here, right? But a11 times c1 contributes to it. And in the second column times in the second row times the first column, a21 times c1 contributes to this, and then a bunch of other junk, right? So you can clearly see a pattern where, like, because in matrix multiplication, when every row is being multiplied with the c1 through c, and only the first element is being multiplied with c1, then you get like c1 a11 plus a bunch of other junk, c2 plus a21 plus a bunch of other junk, and then c2 times a21, and then etc. through cn times a1 plus a bunch of other junk. And then assume the other stuff just lies there and you don't care about it. Then you know that, this is c1. And it's just c1 times a11 through an1, which is just the first column of 1. And then you can think about c2 times the second column of a the same way. If I could draw a nice diagram, perhaps that would be nice, but at the moment I'm too lazy to do that, so I'll draw a very not nice diagram instead, because this one's probably like not very intuitive if you haven't taken the time to think about it, which I suggest that you should. So yeah, so I think like this diagram sort of represents what's going on, because the dark blue portions get multiplied by the dark blue entry in the column, and the light blue portions get multiplied by the light blue entry in the column, and so on. So I think that's how you look at it. Obviously that's cheating because we haven't defined what it means for you to have a matrix and multiply by a vector, but you can think that's what it means. I think you can derive it by understanding that the matrix is defined by the linear transformation as well as the basis you choose, and once you do that, then the definition of a matrix multiplying by a column naturally follows from those basis and linear transformation that you chose. So it's not too difficult to do that. I just don't think I can have the energy to do that right now. Certainly not worth it for a question like this. Suppose A is an m by n matrix and C is an m by p matrix, and show that you have, oh shoot, I actually haven't looked at this question yet. Yeah, no, sometimes you just look at a math textbook and you try to think about all the questions in your head, and they'll become a blur, and sometimes you just miss one or two and you didn't even realize. But maybe with all these questions I did, I can just like do this one. Doesn't seem impossible. Okay, so we got two matrices. One is m by n, and the other is m by p. Okay. And then prove that the jth row of AC is equal to jth row of A times the entire matrix C. Oh, I didn't know they defined vector times matrix. Wait, I mean, if they already defined it, why did I struggle so much? Because I could just use the definition. Okay, no. I completely missed that. That's my bad. Okay. So, first you gotta recognize that what produces the column of AC, the jth row of AC, let's say, right? Let's say this is a matrix AC, and this is the jth row of it. And I think previously defined in matrix multiplication, which I forgot how exactly it goes like, because it's sometimes difficult to remember things like this. Fuck. I think let's take a look at the first column of J row, first column, right? Now what you have is, I think, the jth row of A times the first column of C. I think that's how it's defined. And think about it this way, like if you bring them together into the same picture, this entry is just where they overlap. I was thinking about matrix multiplication. That may make your morning a lot easier. Having to go to class and listen to a professor maybe drone on about 30 minutes of algebra without drawing a single diagram. It can be sort of infuriating. And no, like they come from the best place in terms of intention. They want to be accurate. They don't want to lose. Sometimes people say that geometry is the soul of mathematics, whereas algebra is a cold-hearted machine where you replace the soul and in order to get results. So sometimes you have to go back to the soul, right? You have to go back to the geometry. Otherwise, you lose a lot of understanding and intuition. Unless you're like a genius level mathematician, in which case I don't know why you're even here. So you can probably think of algebra in your head just fine. Let's think about it like this, right? And let me formally write it out because it's good practice. So the jth row first column of AC is equal to, and it's probably gonna be some jargon. Everything on the let's say jth row of A was a moving iterator R going from 1 to what was the dimensions and times P. So the matrix that is going to end up is M times P, so up until P times yeah, the R's column of C and then row 1, right? I mean, this is fine. ACJK is equal to, yep. Okay, yeah, that makes a lot of sense. And then you just derive the generic version, or not derive, like intuit generic version, like that. Yeah, so the rho J of AC equals to rho J of A times C, right? I think that's quite reasonable, because what you've done here is you've taken the jth row of A and then you're just multiplying by every column of C, and that's how you arrive at this particular column of AC. There's nothing too bizarre about it. Perhaps like if you're doing this in a homework, you would want more mathematical language, whatever you want to call that. Alright, suppose A is a 1 by M matrix and C is an n by p matrix. And you wish to demonstrate that a vector A times a matrix C is equal to this. I want to show that AC is a linear combination of the rows of C as the scalars and multiply the rows coming from A. Okay, I mean, this is probably to prep you for the dual space work, because when you think about duals, you usually get column times matrix or vector times a matrix. When you think about the regular matrix represent linear transformations or linear maps that are not duals, you usually just go from matrix times vector. I mean, it's good preparation, I suppose, but it's not healthy for you to attempt to read 125 pages of mathematics in, say, 6 or 5 weeks, because even so many people do it, they don't really understand what they're reading, and they don't really have the time to. That's the problem with, I think, most of higher mathematics education is people don't really know what they're reading. So, yeah. I'll take a pause here because I think the video is already too long, and I'll make another one later.